Dans le bon sens? Je vais regarder sur la vidéo. Merci.
Hello guys, good afternoon. There are still several seats here on the front if you are welcome to, if you want to come, because the screen is relatively small, there is contrast issue, so you are welcome to come here, okay? All right, did you guys have fun? Yeah. Oh, come on, did you guys have fun? Are you learning? Okay. That's the most important thing. It's nice if you are winning, and we will know soon who's gonna win this competition. And I want to remind you, there will only be one winner. It doesn't mean that you have 23 losers. You are all here to learn. Okay? And that's the spirit and the mission of Formula Studio. All right. I would like to speak to you about the classical mistake that I see too often being made in Formula Student. This is Formula Student 160 for me. So I've seen a lot of vehicle dynamic and race car engineering. And I want to tell you one thing. As much as I'm known to be a very demanding judge, there is not one mistake in vehicle dynamic and race car engineering that I have not done. Okay. In 1979, I designed a race car, designed and built a race car and wind tunnel for the thesis of my engineering degree. I don't come from a I come from a pretty dysfunctional family. I didn't have any moral support. I had no money. I actually days that I was really hungry. And I don't consider myself as a smart guy. I had to work really hard to have some grit. But when the passion is there, I designed that car. The school gave me a 19 out of 20, which is a score that they hadn't given for 17 years. And the director of the school said, wait a moment, we have a race car, we do not, let's make a little press conference. Journalists came, an article was written, and because of that, a few days later, I was about to sign a contract to work for a petroleum company, which I knew was going to be a boring job, but I wanted to do it because I had to put food on the table. I received a phone call saying that I was the award of prize of innovation from the second biggest Belgian company. With an inflation of 3%, today that would be 845,000 euros. And at 23 years old, I became a race car manufacturer. Hey, they gave me a 19 of 20. I know everything. I didn't know shit to speak English. I made all the mistake by redesigning this car. So that was the beginning. And then I worked for 5 years in the World Touring Car Championship. I worked for 3 years in Formula 3, then in Formula 3000, which is Formula 2 here in Europe, then in Japan. Then I came back to Europe, I worked in Formula 1, and then I worked in IndyCar for 5 years. So mainly half of my career was race car engineering. And I had a few success also. I don't know, this is an article they wrote in a magazine in Japan. I don't know, maybe they say I'm from the mafia. But And in 1997, I created Optimum G. Optimum G has 3 main roles. We are teaching tomorrow in transport in front of the Transpolis. I'm teaching seminar number 358. 16,200 people came to this seminar in 28 years. And we do consulting in the race car and the passenger car industry, and we do simulation software. All right. And then accessory also, I've been a design judge in many different opportunities. I need to correct that because I started in 1996. So, and I give several university courses in Europe, USA, Australia, and South America. And then I just add France as one of the countries that I visited recently. Okay, let's go to business. Some basic design errors you should and you can avoid, which are illustrated by mostly pictures taken at Formula Student competition. This one. So it could be that you will recognize your car, the details, so that probably only you will remember to say car X is good and car Y is bad. That's not the case. All right. What's the problem here? If this thing breaks, where do you think it's going to be breaking? Right there. That's what we call rodent in bending. Forces are not supposed. Oh, guys, you take as many pictures as you want, no problem. I want you to know that this is recorded, so you will have that, and I will give to the organizer the PDF of this presentation, and it will be for you. Okay, so you take as many pictures as you want, but you're gonna have yeah, okay, so, forces are not supposed to travel in zigzag. You should have something like that. Make sense? Yes, I know there is a problem. The problem is that the rim can touch the arm of the wishbone. Well, that's your problem. There are people who can do that without having the arm touching the steering wheel. The steering arm, so without the rim touching the steering wheel. Okay, that is better. I like this. You have the extension of the 2 arms of the wishbone going through the top wishbone rodent. I would have preferred here to have the tolling going through there. There is a little S there. As I said, force are not supposed to travel in zigzag. There is a good one. It's not because it's carbon. That's not necessary for me. But you have here definitely the extension of the wishbone axis crossing at the spherical joint of the top wishbone on the upright. Another thing that you have to understand, if you can make a car with a push or pull rod. So let's go step by step. The pickup point of the push rod on the wishbone. The pickup point of the wishbone on the upright. I went too far. The pickup point of the wishbone on the push rod on the rocket, the center of the rocket. The pickup point of the damper on the rocket. The pickup point of the damper on the chassis. The pickup point of the droopling on the droopling of the anchoring bar on the rocket, and the pickup point of the droopling on the anchoring bar blade that you cannot see because it's under the hidden behind the bodywork, should be absolutely the same plane. Okay, it can have 1 or 2 degree misalignment. But imagine you have a push rod like this and a rocket moving like that, you are going to introduce compliance. Okay. So, as I said, all these points should be in the same plane. That's a very basic principle. Okay. You have an example here of a pull rod, for example, here. You have a wishbone like this, and as you can see, the pull rod is not bouncing. And guess what? If this thing is breaking, it's going to be that. That's the reason, by the way, they had to have so much fixing. I will explain to you, if I have the time, how to make a good car, which is at the same time light, and safe. So that is a thing. And unfortunately, and I will demonstrate to you, these kind of basic principles are not taught in school anymore. I'm going to be very clear with you. You're not going to like what I'm going to say. But here's the thing. You do amazing FEA analysis of shitty design suspension. Because the basic of good design are not taught in school anymore, and you rush to the computer too quickly. When I designed my car, I was lucky to have a very good mechanical engineering teacher. Computer came the day after I graduated, so it was big drawing table, like he drew me. And the teacher looked at me and said, "Claude, put your finger in the weakest part of the chassis." And I said, it's here. And I was right. Not because I'm smart, because I had a very good teacher, and I failed several times, and my teacher explained to me why I'm failing. The guy looked at me and said, "Solve the problem." And then he said, "Claude, look in my eyes." And remove weight. That way, guys, that way. Function, then fall, not the other way around. Okay? And the mistake that you guys are doing is that you are looking at pictures of cars on the internet. When you do that, your imagination goes from 180 to 30 degrees. Function, define the function, then the form. Okay. All right, other example. This one. Are you ready? You know, if this was in Spain, I pushed on the car with my hands like this. I didn't jump on the car. And boom, this thing collapsed. So for 5 seconds, shit, I broke the car. And then I realized, wait a moment here. I look at them, you didn't test that car. No, they said, yeah, I can believe it, because the force that I exerted was less than a simple 1G load transfer when you're braking the car. Okay. What was the problem? Well, you have the juke link of the push rod and the damper. By the way, the same issue that I see with people who are using a Z-bar. You are going to have the line of action of the juke plane of the entry bar are not in the plane of the push rod and damper. You are creating compliance. Okay? I want you to remember this. Compliance is the enemy of the driver control and confidence. One day I calculated that between the steering wheel and the two front contact patch, there is 24 springs in series and 24 dampers with hysteresis. Your steering column, everything is bending. The only thing you need to bend is the tire, because no slip, no grip, no deflection, no grip. Try to run a car with steel wheels, no way. Okay. But the rest shouldn't be. Do you know that on a 10-inch rim, you have a 0.4 degree of camber per G? So you take 2 G in the corner, your kinematic is already wrong, your camber is already done by 0.8 degree. And believe me, also, there are many forces. Guys, you have seen this video of several balls in steel, one by one, with 2 cables, and you with one bolt and conservation. Okay? Now, do you imagine that between each of the balls you put a 1 millimeter rubber? Will it take time? Huh? If there is one thing that students do not understand is compliance. You want an example? Pull rod. I'm a fan of pull rod on the principle. Why? Because you put a damper lower CG. By the way, to make a good time Formula student, there are 3 principles. The lightest car, the smaller CG, the lower CG, and the lowest yaw inertia. Okay. And the cheapest car to make a light car, the cheapest way to make a light car is to make a small car. Okay. So these people, what they did is that with a 10-inch, very difficult to put the pull rod very vertical. Okay. They did put dummy damper and dummy wheels. And they load the car. There's no need to put 2 tons. The goal is not to break. They loaded the car with sandbags representing the downforce that they had, a bit of downforce, and load transfer distribution. You heard me. Solid wheel, solid damper. The ride height changed 3.5 millimeters. But when you put push rod, much easier to contain a vertical force on the wheel with push rod, which is nearly vertical, than the pull rod, which is nearly horizontal. Right? Just a question of concept. All right, I'm going to accelerate. You have an example here where, in my opinion, you are going to create an unnecessary reflection. The wishbone axis shouldn't go through the node of the chassis. It speaks for itself. You have an example here which is a catastrophe because not only the line does not go through the node of the chassis, but there is also a leverage here which allows this lever to, there is a double reason for deflection. And the guy said to me, oh, Claude, we were on the FEA, it's only moving 0.15 millimeter. Oh yeah, 0.15 millimeter there, and 0.1 there, and 0.15 and 0.2. And then you have a succession of mushroom there, and the car is not reacting. Okay. All right, you have an example here. This is a drama, and unfortunately, I saw many cars like that. You cannot put a pickup point of any suspension anywhere else than at the node of the chassis. That is super basic design. Okay. You determine the suspension point, then you go to the frame. Actually, the frame, the chassis, or the monocoque should be one of the last things that you draw. Because it takes the pickup point of the suspension, the pedal box, the anchorage of the battery casing, your seat belts, and so on. Okay. All right, that's another one. Okay, I'm not going to be picky, but I have to wonder why this little tube had to be added here. But all right. That's another one that I saw here. Let me tell you this. When we still had combustion car in many racing Formula C or Formula C, there was a German team who made an amazing internal combustion engine with 92 horsepower. Really fantastic. And when they accelerate for the first time, the chain bearing, because the support in aluminum that hold the differential were attached in the middle of the tube. It bent and the chain bearing. You understand that? You cannot have the attachment of the plate that support the differential anything else than at a node of the chassis. Another one. This, for example. And this one. And you are proud of that? Yeah, I know. Yeah. Here is Judge. Here is Exhibit A. Can you hold it up? No. I believe. No. Listen, I believe you can make something with minimum compliance. That's another one. So it's a big compliance. All right, let's look at this. You have here the push rod. Look at that. This push rod is going to act on the lower wishbone, and the push rod do not pass through the ball joint there. What's going to happen? The wishbone is going to be bending, correct? So you have a spring on the spring on the spring on the spring. Again, the push rod axis should have gone from the ball joint of the lower wishbone on the upright. That's another one here. Forces are not supposed to travel in zigzag. It's that simple. This is correct. It's nice. And it's not because it's carbon fiber. You have an example here where the push rod is attached to the upright and not to the wishbone. There could be some ideas there in terms of vehicle dynamic. I'm not going to go through that, but that is a decent design. That's another one, guys. Listen, guys, I hope you are listening to me. Single share is a crime. You cannot use single share. It's a source of compliance. Okay. You want me to tell you a story? I'm working in Japan. We test a new car with exactly the same setup. The driver went out and he said the bar of the car is going all over the floor. We are grinding the floor. I called the guys in England. Does the new wings have so much downforce? Said no. So we started with the same static radar, the same type, the same tire pressure, the same setup that we had the year before. Okay, and the car was grinding the ground. So we made a test again with dummy spring and dummy wheels. We pushed that, then it's much more load because that car is much more done for. Are you ready for that? It was the rocker which was bending. And why? Because it's single share. And that's it. Single share should not be. By the way, this is forbidden in Formula SA. The toe link cannot be single share. Okay. That is decent. That is double share. That's what you should be doing. Okay. Another one here. Look at that. The difference between the two. There is no play on this one. What's happening is that, yes, you're going to tell me the push rod and the damper, or the pull rod and the damper are the same axis. So there is no need for play. Yes, except that necessarily you're going to have some compliance. And then there will be a side load. And therefore, if you don't have play, you're going to have friction. So you have to have a side play in the attachment of the damper. That's another one. You cannot have the pickup on a rocker in the middle of a tube. This is disgusting. There have been people who have been executed for less than that. Okay. Now, I'm joking, but seriously, a bunch of 15 years old playing making a goal count and so on, that's fine. But not from an university, not from an engineering school. That is not allowed. You should know better. Okay? All right, that's another one. This is absolutely ridiculous. You see that you have a big leverage, which is going to put a torque on the tube there. Not a good idea. Pick a point in the middle of the tube. Okay? That's another one. Look at the size of the rocket. Are we in Formula Student or Formula Truck? Okay. No, there is no need to have it that big. Okay. If you divide all the dimension by 2 or 3, you still have the same ratio in the leverage of the rocket itself. Okay. All right, that is clean, very light, very stiff. Makes sense? All right, bigger is not better. Try to make it light, stiff, simple. Make it compact. All the mass is close to the center. That's another one. I want to remind you that an actual bar is supposed, a U-bar is supposed to work in torsion, not in flexion, correct? And that's what's going to happen here. Okay? Plus, when I look at the support of the actual bar, guess what? You're going to have on the car an actual bar stiffness at the wheel, which is 10% of the one you calculated with here, because the installation is correct. All right. This is bad also. If you look at me through the top, you have a big distance between the bearing, which hold the actual bar, and that distance there. Okay. It's just simple. And by the way, you will notice that the drooping here is actually single share. Okay. And by the way, the bearing that holds this U-bar should be arriving at a node of the chassis. Again, the chassis should be, if you have a tubular frame or monocoque, it should be designed at the end, when you have all your pickup points, including the one which hold the bushings of your actual bar. That's ridiculous. You have an actual bar here, which is nearly as long, as wide as the car. Yeah, you can see that. And look at this. On top of that, the drooping, I'm going to make you a bigger picture of that. The drooping of the actual bar is arriving in the middle of the tube. So it's a spring on a spring on a spring. That, you have an example here, where you see the actual bar here, which is on the rear, near the differential. And this the actual bar, look at my hand, it was big like this. And it has the same speed that the actual bar, which was nearly as wide. Okay. Another one here, Z-bar, same thing. I have a problem with that because you are introducing undesired compliance. No, look at that. Another one here. 1, 2, 3, 4, 5, 6 tube, and 2 nodes which are 80 millimeters apart from each other. There is a simple rule when you design a tubular chassis. Minimum tube, minimum node, and maximum triangulation. Okay, that's very, very clear. It's unnecessarily complicated. This upright, for example. I saw this upright here in Formula. Yeah, this one is green. So you say, that's me. Yeah, it's very cute. I've seen better, but this one is very good. I have to say. Well, there is always something better than you. But this is a cut of this is Formula 10 again. All right. Look at that. I took a tape measure, and I measured the length of this push-rope. It was 712 millimeters. So it's guaranteed buckling, correct? Okay. And then there is another one I want to show you. This one here. When you are in a home and you are cooking an omelette, okay, you fire it in, you put a little butter of oil, but the fridge will not be in the bedroom, correct? Why would you go to the bedroom, take the eggs and come back and crack the eggs there? Well, I have the same question for you. Why do you take a force which is starting at the bottom of the tire, sending it up for the spring, and going back down for the end roll bar at the bottom? It's unnecessary length, unnecessary weight. Okay. That's another one. Why in the hell do you have this screw so long? I know there's a rule that you have a certain amount of thread that you have, but it doesn't have to be that long. You know, but I know you're going to tell me, the Claude, if we cut that, it's only a few grams. Okay, yeah, but that gram in your account, which is stupid. And more than that, guys, it shows to the judge that you don't care. People buy stuff first with their eyes, and when they see things like that thing, what do they care? All right, a few more. Here, look at that. That's the typical mistake. Okay, all right. I need to make a little demo here. Some of you have seen me doing this demo. Would you mind to come here? I need a person here. Imagine that this is a door. This is a door. You see that? Okay. This is the hinge. Okay. I'm mad at you, and I want to enter in your office. Okay. Show me with your finger what you are going to do to prevent me, to push the door to prevent me to open it. No, sir. I was hoping he was going to give a good example. All right. Come on. Yeah, you agree that it needs to push here, correct? Push here, it needs to have the, okay. So you need some education, IPG there. No, but seriously, and so no, do you agree with me that the force needs to apply at the edge of the door and perpendicular to the door, not with an angle? Why the hell in that case do you put, and I'm going to show you several pictures of that, why do you put so little distance? Look at the next one here. So little distance in the tolling. You see? So little. And then the guys, of course, the upright will be slightly longer, but you save so much. You should use all the space that you have in the rig to have the largest steering arm, front or rear, to diminish the load, right? And then that's how your rod end, instead of being 8, becomes 6 millimeter. Your tube of 22 by 2 can become 18 by 1.5. Okay, all right. And then, so all these things, the tolling must be perpendicular to the plane of the wheel or the longitudinal axis of the car, and it has to have the steering rack. And the guy said to me, oh yeah, but then we have to change the steering rack ratio. Yeah, my friend, you make the design of the upright, then you choose the steering rack ratio, not the other way around. And so there are many examples. The contrast is not necessarily very good, but you will see that there is so much space that you can use to do that. That's another one that I noticed. I mean, this thing is going to be very fragile. It was a drawing; it didn't see on the car, but it's another example like this. Okay. All right. Here again, I saw so many of these cars, with a steering rack which is too small and which has an angle from part to the longitudinal axis of the car or the plane of the rim when the steering is here. And it shouldn't be like this. Okay. And voila, here, so many of them. Okay. All right? So all the pictures have been taken here. Okay. That's another way to understand how the CV joint on the steering torque displayed. The angle on one side should be the angle on the other side. I don't have the time because this is not a vehicle that recalls, but go on the internet and you will see how the CV joint needs to be aligned. Okay? That's another one. Can I tell you something? When a judge wants to decide if the car is going to go in the final or not, he asks himself two questions. If I had to buy a Formula Student car, would I buy this car? Or if I wanted to drive a car, should I drive the car? And there are some of the cars here that I would love to drive, but I will never buy them because I know that it's going to cost me a fortune in maintenance. Okay. When you have a mess like that, it doesn't play well. Okay. Can you reassemble that very quickly? Okay. And there are so many pictures like that. Your car is a reflection of your team. If you don't care about your car, why should I? Okay. All right. That's another one. Guess what? When you have a radiator like that, the efficiency is going to be necessarily very bad. Look at that. Where do you think, on the yellow cycle there, where do you think the air is going to go? Like this. The path of less resistance. Okay. There's another one here. You have a huge radiator with a fan which is only using 1/3 of the surface there, because the whole thing is in a side pocket, which no ducting. Let me show you a good example. That's another bad example. You see the radiator is here. The air is not going through the radiator. It's going to escape like this. There's a good example here. This is from a university in England. The guy explained to me that they made a ducting with a conversion diversion, with gas, nice duct going into the radiator and getting out. It cost them 460 grams, but they gained 2.6 kilo because they didn't have a big radiator. The guys working on aerodynamicists will tell you that if we could escape radiator, you'd get more downforce and less drag. Okay, so smaller radiator, less water. And the electrical motor was a smaller fan, which was consuming less power. Okay. All right, that's my presentation for today. But we have 15 minutes. Thank you. We have 15 minutes. I'm going to do Q&A. If after you want to see here, if you have a specific question, you're more than welcome. I'm going to do here in 12 minutes this simple thing. The case about weight. Okay, are you ready, guys? All right. Why and how to include minimum weight as one key parameter in Formula car concept and design. Please. All right. I'm going to give you an example. That's the time where we were using combustion engine. And you see, you can use optimum lap for that. No advertising, optimum lap is free of charge. Okay, you have here the power and the lap, and you see that between 30 and 50 horsepower, you have huge difference, but between 90 and 110, very little. Okay, and I have to ask, do you need 90 horsepower to be competent in competitive performance? Look at the weight, guys. It's in a straight line. That's it. Okay. The first thing is to make a light car, and the cheapest way to make a light car is to make a small car. I don't understand why you would have a wheelbase more than 5 mm, the minimum requirement. Okay. All right. So what is your reduction limit? And what if I tell you, hold on, guys, that wing is coming. How what is your reduction limit is in your imagination. Okay, so I'm going to give you a perspective. Here we go. You have a plane which is able to make 4,000 miles or kilometers, miles, okay. And you ask the pilot to do 50% more, 6,000 miles. So the guy is going to tell you, I cannot do that because I need bigger fuel tank, okay? Bigger kerosene reservoir. And then the guy said, well, I cannot take off. Why? Well, because the airplane is heavier. What do you need? I need to have a bigger engine, okay? Okay, you give a bigger fuel jet, and then the problem, this thing is more thirsty, so you need more fuel, correct? And you see the crescendo, make sense? So you look at me and say, what's that to do with vehicle dynamics? Well, the next line is going to show you. Application of the 2 Newton law, F equal ma and action equal reaction. Imagine that you have a car which is 200 kilo, which is possible. That means a 140 kilo car with a 60 kilo driver. And that car takes 1.5 G. You agree with me that F equal ma, you're going to have 1,000 Newton, and the sum of the Fy on the tire will be 3,000. Know that you have a car which is 50% heavier, 300 kilo. F equal ma, if you have the same natural acceleration, you increase the mass 50%, the force will be 50% more, correct? Makes sense? So guess what? Which is not guaranteed because as you know, the coefficient of friction decreases with the vertical load. Okay. So now you have 4,500 Newton total. And I'm going to take an example of the upright that you have on the right rear. And you agree that on the car which is 200 kilo, you are going to have some blue color. And on the car which is 300 kilo, you're going to see some red color. You can be the champion of design and make the rib of the upright right in the direction of the force coming in. But if that force increases 50%, you cannot have the same thickness, correct? And we are going back to the same sheet, which is the heavier it is, the heavier it will have to go to be. Okay? So there are 2 solutions. You have more material, therefore you have more weight, therefore you are going to have the heavier the car, the heavier the car will have to be. Okay? Or instead of working hard, you work smart. So let me give you an example, a simple example. Top view, that's the car, like the wheel like this. Let's say your wishbone like that. You agree that if you have a lateral force, only this link of the wishbone will work. And if you are braking like this, only that link will work, correct? Wait. But if you have a wishbone like this, you agree that that force is going to be separated differently. You're going to have that one in compression and the previous one and the front one in extension, correct? And you can have the free pickup point of your wishbone in the same plane. That means you have the same anti-dive, the same rolls and so on, but by displaying the force differently. Make sense? Okay. If you want, you can go on LinkedIn, you type my name, and you say road cases. Okay, there are 3 posts because LinkedIn doesn't allow more than 1,250 words, where I explain step by step to make you road case. How does the guy who designed the chassis and the guy who designed your ride how can he do something light and stiff if you don't tell him the force at each of the pivot points? Okay, and then you take the coefficient of safety of 2. The people who take the coefficient of 3 is just to be sure, because they haven't done the calculation earlier. Okay, all right. And you know, when you think about that, the guy who designed the chassis goes inside out, and the guy who designed the suspension goes outside in. And where do they meet? At the pickup point of the aircraft, on the chassis. So that's things that you're going to have to take into account. All right. Now, that is a good example. That is a bad example. I'll show you things like that. Okay. See, this thing will have to be heavier, correct? So, all right. Now, I want to tell you this thing. I will never forget. Formula student in Germany, 2011. The team authorized to tell me who it was. You have here Team A, which was Delft, and Team B was Rico. 80 kilowatt, 4-wheel drive, no wings, 145 kilo, to road tubular chassis. Team B, 82 kilowatt, big deal, 4-wheel drive, no wings, tubular chassis, 230 kilo. So I said to the guy of Zwickau, guys, how is it possible that you have a difference of 85 kilos? It means more than 50% for the same concept. And they told me, well, last year the car was 265, we gained 35 kilos. Good for you, but that's not my question. And we go in the conversation, listen to that. At a certain time, the guy from Zwickau said, Claude, if you put the battery of Delft in our car, we cannot finish the intros. Ah, yeah? Why? Because we consume more energy. And why? Because the car is heavier. The consequence is actually the cause. Okay. So, same concept, but okay. And I'm going to give an example. The car B is heavier because it's heavier. More weight, more battery, more weight. The lighter the car is, the lighter it can be. The heavier the car, the heavier it will have to be. And may I propose to you a complete different approach to your weight of your car? Instead of taking this your car and diminish the weight by X kilo or X%, or having the same weight as the winner, I want to propose you a different approach. You start with a white sheet of paper and you increase each one of the parts a minimum. And you cannot do that unless you think form, follow, function. That way, form, follow, function. You have to define the function like your road cases, then you are going to decide your form. And I remind you, you can have the same forces and moment on the tire, giving less load on each of the linkage and less load at the X, Y, Z pickup point. Fx, Fy, Fz pickup point. Okay. All right. So this example here, guess what? The team of Zwickau, they had all 80mm road ends. And the team of Delft, are you ready for that? The low wishbone inboard 5, outboard 6. The top wishbone 4 on the inboard and 5 on the other. And the toe links were 3mm. Yes, sir. It was looking like the toe link of so the same acceptation of risk of failure compliance. The lighter car has less force, so it doesn't need to be that strong. Does that make sense? And you know, it's not only in Formula Student. Look at that, the Golf 1 and the Golf 7 in 2018, 10 to 15, 20, neither double doing. And all the job that the guys have done on aerodynamic and on combustion engine has been killed because of the weight. Where do you consume the most? On the autobahn, on the freeway, on the road, or in the city? In the city, correct? So the heavier the car, the more fuel consumption. Okay. All right. Yes, there are some of the things for safety. You don't discuss that. But of course, everybody wants the 7-head speaker. They want to have the heater in the seat, and so on. What is the cost for that? Okay. An example is this: when the new A3 came on the market, they were 15% lighter. And you know. The guys at Airbus, for example, I have a friend of mine at Airbus, he said, we have a thing which looks like a tolling, literally like the tolling of Formula Student. All carbon, the weight has been divided by 8, 12.5%. Okay? Because for them, every kilo you save, you are speaking about million of dollar of or euro of kerosene. So let me ask you, if you are a boy, which girl do you prefer? and if you are a girl, which guy do you prefer? Okay? So let me which upright do you prefer? That one or that one? Okay? Guys, I'm gonna finish by that. It is possible to make a car, please. It is possible to make a car which is at the same time simple, light, stiff, aesthetic, and cheap to manufacture. And I want to finish with one thing. When I designed my first car, I designed it upright, and I was so proud, and I went to show it to my engineering design teacher. And the guy looked at me and said, "It's not sexy." I mean, sexy. And he said to me, Claude, everything which is at the same time light and stiff is beautiful, pleasing to the eyes. You know that if you have a hub with an angle like this, you know that you're going to have a lot of red color. Okay? Do you know that an egg, if it's positioned properly, can sustain a force of 40, a weight of 45 kilo, correct? The egg has been designed by the function. Okay? Because the chicken and the egg falling this way, not the other way. Okay? All right. So that's it, ladies and gentlemen. Thank you. The last thing I want to tell you is to share my congratulations to the team who organized Formula Ski in France. France is young in Formula Ski. That's only the third edition, where I just went to the 21st in Brazil. And FSA started in 1981 in the United States. But I hope they can catch up. And one way to catch up is to apply very simple engineering recipe. Thank you.
Hello. Hello. Encore. Je laisse encore. Encore. Ouais. Ok.
En cuanto a la cámara del laptop. Yo sé, güey.
Hello everyone. Hello everyone. Welcome to this award ceremony. First, I would like to thank Claude for this quick lecture that you gave us. Thank you, Claude. I think we can applaud him one more time.
There is one thing I forgot to tell you. There are something like 10 hours of video that you can, if you type Optimum G, you can have all to choose a damper, how to choose all these videos are free of charge and accessible to you. And go to LinkedIn, and I gave time to. Thank you.
So first of all, you have probably seen me along the track and trying to bother you with flags and with everything. My name is Mathieu. I'm the event manager of Formula France since the beginning. And thank you. Formula France started in 2023 with all the French teams, and then became international last year in 2024, and we are now at the end of the third edition, and I'm quite very happy to have managed it with Robin as well, who joined me last year to have organizing this. Thank you, Robin. This event could not have been possible without all the volunteers. We were 80 this year to organize this event, and I'd like please teams to make a round of applause, big round of applause for all the volunteers who helped us to make this event happen. Also, we have volunteers, but we also had sponsors. And again, I'd like a big round of applause for all the sponsors that helped us making this event happen. Thank you. Now, that this short introduction has been done, we will go to the actual prices, and we will start with the static awards, if you like. But before I announce any static result, we have a quick video to show you.